Okay, in last Friday's lecture, we have already derived the per unit length equivalent capacitance, per unit length equivalent conductance, and inductance for coaxial cylindrical arrangement, which contains two conducting objects, two cylinders, concentric cylinders, two conductors. So in this arrangement, we know that the per unit length capacitance, inductance, conductance are only related to the geometry and material property. So as you can see from these three equations, the capacitance, conductance, and inductance, they are related to the ratio of outer radius over the inner radius, and taking the log value of that and times corresponding material property, such as permeability for inductance, permittivity for capacitance, and conductivity for the conductance. Interestingly, if you do some manipulation over the L, C, and G values, say taking the product of L and C, you found that the influence of the geometric parameter can be cancelled out. It only lives with mu times epsilon, the product of permeability and permittivity. So the LC value, the per unit length, inductance, capacitance, and conductance, they have same relationship that is irrelevant, not related to the geometric parameters, and only related to the material parameter. So as you can see here, we have two critical relationship, that is the ratio of G over C, conductance over capacitance, equals to the ratio of conductivity sigma over epsilon. And the product of L and C equals to the product of mu times epsilon. So the direct consequence of this result is that as long as you can calculate or derive one of the three parameters, then the other two parameters can be found by using this relationship, providing that you know the material property, say sigma, conductivity, permittivity, and permeability. All right, so you don't need to calculate all the three per unit length parameter. You only need one, and you can use the material property relationship to find out the rest of the two parameters. So it's a kind of a useful result. However, I need to notify that this relationship is only valid for homogeneous materials, so that in the environment of this two conductor arrangement, the surrounding material should be homogeneous or largely homogeneous. We can see some other examples later on. So in table 5.2, it lists the per unit length capacitance, conductance, and inductance of some commonly seen or some simple two conductor structures. First one is the parallel plate. The parallel plate is characterized by its width, 宽度了哈，它的宽度，还有它的那个两个板子，平板结构的两板间距 D。而这个答案是在另外一个条件是 D is much smaller than W. D is much smaller than W to satisfy this parallel plate geometry. So as long as the height of the two-parallel plate is much smaller than the width, then the per unit length capacitance is epsilon times W over D, sigma times W over D. So you can see that the same geometric relationship can be found for conductance and capacitance. On the other hand, for the per unit length inductance, for the parallel plate structure, the value L equals to mu times D over W. So the geometric relationship is inverted. So if you take the product of L and C, you will end up with epsilon times mu. The D over W part is cancelled out. Similar result as we have already seen for the cylindrical structure. Coaxial cylindrical structure is listed in the second row. So here is the capacitance, conductance, and the inductance. The same relationship can be found for capacitance and inductance, as well as for capacitance over conductance. So this is a cylindrical structure. Table 5.2 also lists other three structures. One is the pair wire, who will be discussed more closely in today's lecture. In today's lecture, we will cover up the per unit length capacitance calculation for pair wire arrangement. That is, two wires with radius, with certain thickness, separated with a distance of 2d in the space. The other is this one is the so-called eccentric inner conductor 就是像同轴线，但是不是同轴线，你可以说它是被踢了一脚的同轴线，把它给踢歪了所以你看到它是不同轴的所以它的那个内径跟外径分别是 A 跟 B， 但是内径的圆心跟外径的圆心距离了一个 D 所以它可能是一个被踩了一脚的双柱结构所以你不能叫它是同轴线，因为它歪掉了那它对于这种结构的话，其实你也可以算出来它的所对应的那个对应的 per unit length capacitance, inductance and conductance 那这里有一个，你看到这里有一个三角函数，叫做这个是什么 ？arc hyper cosine， 好吧，后边会念复音就表示 arc 后面那个 h 就是 hyper cosine， 所以 arc hyper cosine 也就是 hyper cosine 函数的反函数。那你还会用计算机按，好不好？练习一下，回去做练习题，作业练习题自己练一下要会用计算机把 upper hyper cosine 这个东西按出来 ，OK？ 然后第三种的话是这个啦，有金属层保护的 pair wire， 所以它基本上是 pair wire， 但是它外面还有一层金属。那在实物上这样子的传输线结构也是会被用的啦，也是可以被使用的。那为什么要有这个金属保护？有至少两个原因啦，一个原因是让那个线感觉它更有强度，OK 有保护嘛那其实像那些什么海底电缆海底光纤其实都有某种程度的保护啦对不对但是有的时候人家故意要把你切断的话其实这样薄薄的一层金属保护可能也不是很足够所以一个是给它物理上面的保护，另外一个是给它电磁波上面的保护也就是说这个是传输线，所以你要么是传能量，要么传讯号。那只是说虽然是传输线结构，但是你假如没有什么保护机制，像这一种镂空的话，那其实能量是，假如你的结构有一点变形的话，那能量就有可能会，能量或者讯号就可能跑出去所以 金属保护的这一个层，它的另外一个目的是，避免它讯号外漏，然后避免这一个传输线被干扰啊，也就是外部的讯号打不进来，内部的讯号也跑不出去啊，所以是它的金属保护层的目的。那这个我们看到一些常见的 transmission line type 哈，那当然这些看起来都是。好了，很多是老古董了哈，但有些还是在应用的哈。像左边这个口味秀，啊，这应该蛮贵的哈，因为你看到它的那外面的那个金属层其实是实心的哈，所以然后里面的那个铜柱也是实心的哈，所以这看起来就比较高级哈，应该是比较贵。那你只要去看一般市面上的那个。第4台的缆线啊 ，coaxial cable 的话，拆开来外面都只是一个金属编织网啊，来去节省成本。然后再来是像这一个啦 ，low loss dielectric， 有没有看过这种传输线？有没有看过这个？没有哈。我小时候看过，我小时候看过，我在10岁以前，有一个台湾，我看台湾的电视大概是民国50几年开始的。我小时候，民国60几年的时候，我有看过这种的。那个时候的那个电视天线，电视机跟每台电视机都有自己要连一个天线啊。那电视机跟天线之间连的就是这一种传输线，它是一个300欧姆的传输线啊，300欧姆的传输线。它这个就是我们刚刚。但是现在应该很少看到了啦，哈。那像这个是什么？这个就是刚刚我们看过的，就是有外面金属层保护的 two wire 的传输线嘛，哦。那像这个是 twisted wire， 就是说它也是 two wire， 但是要把它转起来。为什么？为什么？它的目的是防止讯号外泄或者是被干扰。它的目的是防干扰的。这个我们之后会讲到为什么它要这样做啊。但基本上这种叫 twisted pair wire 啊。The purpose of this structure is meant to prevent the so-called EMI EMC 哈。EMI refers to electromagnetic interference 干扰 interference。EMC refers to electromagnetic compatibility。So all the electronic device you have, such as the cellular phone or other electronic devices, before they can be put into the market, they must pass the so-called EMC EMI test for in different countries, in different regions, so that they are certified that if they pass the test, they are certified to be immune to the electromagnetic interference in certain degree, right? And the last kind is this thing. This thing refers to waveguide, 导波管. You have cylindrical waveguide and you have the so-called rectangular waveguide. I bet that you may have not seen this kinds of transmission lines so far, because they are only used for high power equipment, such as radar. The reason that waveguide is used in radar is because they are of low loss. 主要就是它们的耗损小，跟其他的传输线形式比起来，其他的传输线形式那个耗损都是蛮明显的，那个waveguide 的耗损是特别小的。怎么说呢？通常你去看一条传输线，一条 coaxial cable 的规格，它可能会跟你讲说，这条规格它在它的使用频段，它可能1公尺的耗损是1 dB。请问1 dB 是什么概念？或者是说比较正确来讲，就是讯号经过1公尺的这个传输线之后，它会变成原来强度的负1 dB。负1 dB。dB 值怎么算？我看。这个叫 10 log 啦，哈，还有另外一种是20 log。假如你是20 log 的话，通常指的这个是 field 场；假如是10 log 的话，这个是 power。那因为为什么10 log 用 power 用10 log，20 log field 用20 log？ 因为 power 跟 field 的关系是power 是比例于场强的平方，所以它其实会有一个乘平方的一个动作，不过因为我们讲10 log 好了，10 log 里头的 -1 dB 大概是多少？假如你有计算机的话，或者手机上面有计算机的话，你可以试着按一下，-1 dB 大概是0.7吧。我其实没有很有把握这个数字，大概0.7左右。不对，大概0.85，对不起，0.8几吧。我们说0.85好了。也就是说，你只要把0.85带到这个里头去算的话，它出来会是大概-1，你可以帮我检查一下，差不多了，那意思是什么？就是说，你的讯号从这条线的左边进去，右边出来的时候少1 dB， 它的功率就少了打85折。这件事情其实很可怕因为你只要接2公尺雷，那就是原来的功率打85折，再打85折。那你只要接35公尺雷，就是85折再85折再85折，出来的结果大概是一半，0.5。所以说，你这个讯号在这个缆线上面跑了3公尺之后，它的功率就从原来的1瓦变成0.5瓦，再跑3公尺嘞会变多少？0.25瓦，再砍一半，再跑3公尺嘞就变成0.125瓦了。好，那假如只是通讯用的缆线的话，这样的耗损可能还能接受，你这个讯号强度变小。你等于说收到之后再想办法把它放大。当然，对于军用的系统，比如说雷达好了，雷达打出去它的那个脉冲出来的长度，比如说是250千瓦好了。那假如250千瓦的电磁波讯号打到缆线，然后走了3公尺之后，剩下125千瓦。那你要害怕的事情是，另外的125千瓦跑到哪里去了？你左进右出有125千瓦跑出去，那剩下的125千瓦呢，是变成热，耗损在你的缆线上，所以你只要拿缆线去打那个100千瓦、1000千瓦、10000千瓦的那个雷达讯号，那个没多久它就烧掉了，所以为什么要用 waveguide？ 因为它的耗损值很小。再来，它是金属做的，金属做的怎样？好散热啊，所以，waveguide 一般看到都是大功率的系统像军用系统Alright, next we would like to try to we'll look into example 5.7, the parallel wire arrangement. Let's try to calculate the per unit length, capacitance, conductance, and inductance for this arrangement. So we will only find out one of the 3 parameters, say the capacitance, then we can use this 2 relationship to find out the other 2. And this is a more realistic arrangement, parallel wire. As you have already seen, I said that the transmission line for TV reception use 50 years ago is actually just a pair wire like this, right? So let's look at this arrangement. The 2-wire arrangement is composed 2 conductors, 2 solid conductors. So they have radius A, and they are separated by a distance of 2d. And in this figure, you have the remarks of 2d, which is the distance between the center of the 2 conductors. However, you will also note that there is another parameter 2b put here. What's that? Well, 2b is actually the distance between the highest potential and lowest potential among this arrangement. So as you can see here, we have several equal potential circles. Now you have smaller ones and larger ones, and this position is the one with the smallest radius, or you can say it's just a dot. The 2 dot represents the position of the highest electrical potential and the lowest one. So the distance between the two is 2b. And you may have a question, why the 2 points, the radius, the center of the conductor and the position of highest potential do not coincide, are not in the same location. Why? Why? Well, that's because, suppose this is a 2 conductor arrangement, and in order to find out the capacitance, you try to apply some positive charge on this line, and you apply some negative charge of the same amount. And in fact, if you observe the distribution of the positive charge and negative charge, you will find out that they are not evenly distributed. 它们不是平均的分配哦。在这个状况底下，在这个 two conductor 有正电荷跟负电荷的状况底下，其实正电荷会靠右边比较多，左边比较少，而负电荷呢会左边比较多，右边比较少。为什么？ Opposite charge attract， 异性相吸所以在这一个情境底下，其实它的正电荷跟负电荷的聚集就分布上面就会不对称、不均匀，所以这样子的不均匀的结果，就会让它的最高电压、最高电位的位置往这个会往右边偏，这个会往左边偏。我等于是把这个题目的结果预先预告了一下了那我们接下来看怎么样去推导这个结果So to look into this problem, let's begin with a simpler geometry, a simpler configuration. That is the what? The voltage and the field distribution of a single charge line. So here we have infinitely line charge distributed on cylindrical surfaces. Not just a thin wire, not just a thin wire. This is a wire with a certain thickness A. So similar to our previous derivation, let's begin with the Laplacian equation for this arrangement. So this is what? This is the general solution for one-dimensional second order partial differential equation in cylindrical coordinate system. So the Laplacian of V equals to 1 over R times the derivative over R with R times derivative of V over R. And the general solution is this, A times log of R plus B. So this is the general solution for cylindrical coordinate system with one-dimensional partial differential equation. So in this solution, the unknown is what? is A and B, the two constants. So how do we derive A and B? Well, we can apply the so-called boundary condition. Say if there is a position, say R sub 0, and we define that the potential at at R sub 0 is 0 potential, which is you can say it's the voltage reference. So R sub 0 is the position for voltage reference, 0 voltage reference. Then if R equal to R sub 0, you substitute this result into the general solution. And you end up with V equals to 0 because this is the so-called place for 0 potential. So you replace R with R sub 0, you end up with V equals to 0 and it equals to A times log of R sub 0 plus B. Now you have the ratio between B and A. So you end up with B equals to what? B equals to minus A times log of R sub 0. Then the specific solution, so at any other place, the voltage can be expressed as this, A times log of R minus A times log of R sub 0. And because this is a log and this is a minus sign, so it can be simplified as A times log of R over R sub 0. So this is the voltage at a certain place near this wire. However, we only solve for the relation between A and B by assigning zero potential reference. We still don't know the value for A, right? But fortunately, it's enough for us to write up the relationship for E, which is the electrical field intensity, which is defined in terms of what? The minus of the gradient of V. So by taking the gradient of V, you end up with minus A over R. So this is the it's a what? It's a vector. So it's directing to the AR direction. So the E field is kind of emitting out of the conducting wires in axially symmetrical fashion. But anyway, you can write up the expression for electrical field intensity. And next, let's try to solve for the value of A with some known parameters. The known parameter is what? Is the charge density, line charge density on this cylindrical wire. So let's, using the Gauss's law for electrical field, that is the surface, the surface, closed surface integral. The closed surface integral of electrical flux density over a closed surface equals to what? Equals to the volume integral of charge, electrical charge, enclosed by this surface. And because we have a cylindrical wire, and we know that the E field is running in the R direction, and it's only perpendicular to the cylindrical surface. So in general, if we like to apply the Gauss's law for electrical field, the closed surface integral should include three surfaces: the cylindrical side, the top circle, and the bottom circle. However, in this case, we already know that electrical field are running to the R direction. So they have no projection they have no projection on the top and bottom surfaces. So therefore, you only need to calculate the surface integral of D over the cylindrical surfaces. All right, so that's the reason why we have this thing. So this is the electrical flux density, which is the product of electrical field intensity and the permittivity. And what is this part? This is 2 pi RL is the surface area of this cylindrical structure, right? So over the cylinder. All right, so this is the result on the left-hand side. How about the result on the right-hand side? So the result on the right-hand side is the total charge enclosed by the cylinder, which can be found by taking the product of the length L and what? And the line charge density. Line charge density. So it's line charge density is low L0, low sub L0. All right, and the rest is not that difficult because you can check up the result to find that A, the unknown constant A equals to minus of low sub L0 divided by 2 pi epsilon. All right, so you know everything about this problem, including the potential and the field. So by substitute A into the constant A into expression for V and E, you end up with the electrical field distribution and electrical potential surrounding a cylindrical wire. Surrounding a cylindrical wire. So here you can see the V equals to, here right now you cannot get rid of R sub 0, right? It's a little bit bothering because for just single wire configuration, you do not know, some place near the line is referred to as the zero potential reference, but it seems that for the expression for the voltage potential, for the voltage, you cannot get rid of R sub 0. But it is not shown in the expression for electrical field once you take in the gradient of V. All right, so let's go back to the two-wire configuration now. Using the knowledge we acquire from single-wire configuration. So in this case, we have two wires. As we mentioned before, they are separated by distance B. 这题目有点讨厌哦。在这个 configuration 里头，它还是有点简化了哈。你看右边那个图哈，它其实是没有半径的，也就是无限系的带电荷线，有没有？它是无限系的带电荷线，那只是一根带的是正电荷，一根带的是负电荷，所以一根它的电荷密度，线电荷密度叫 low L0， 另外一根是负的 low L0。那注意一下它这个右边的图哈，我就想说，你在学电磁学啊，其实不管电磁学啊，任何的工程学科，你的课本里头最重要的就是图记得把图看清楚、看懂当然，图看懂的话，其实大概课本想要传达的意义大概50%都在里面的那这边的话，你可以看到这个 two-wire configuration 它摆的方式是什么？沿着 Z 轴摆嘛，垂直 Z 轴摆。 那它把它放在其中一条线是放在正 x 轴上，然后另外一条线放在负 x 轴上嘛，哈。然后距离那个 x 等于0啊，就最中心的部分是 b 的那个间距啊。不过这些参数就足够我们来去写出在它邻近空间中的电位啊，邻近空间中的电位啊。那比如说，这个假如是带正电荷线的话，那空间中有一点是在这里，所以它距离正电荷线的距离是 r1，那它 r1 是应该是要一个向量了哈，所以它不仅仅带数字而已，也要带方向哈。r2 也是距离负电荷线的那个距离 r2 啊，所以你会看到右上角的那个红框框是单一电荷导线它在周遭所建立起来的电位表示是啊，那红框框里头的话，它是正电荷所建立起来的电位哈，所以你看到 R0 是放在 log 的分子啊，那前面是正值啊，那假如是负电荷的话呢，你可以把它改成是 R0 在下面了哈。所以套用红框框里头的单一导线的电位，然后用 superposition law， 也就是叠加关系式，写出这两条带电荷线在空间中共同所建立起来的电位哈。所以分别跟什么有关？跟观测点这一点到正电荷线的距离 r1， 还有到负电荷线的距离 r2， 这个负号代表什么？代表这两条线，一条是正电荷，一条是负电荷，哈，所以是一个相减的关系。那既然是相减的关系，哈，它其实是可以转过来。好，那注意到 R01 跟 R02的，其实都是到零电位参考点的距离，所以当它们在共同的坐标系统里头的时候，这个 R01 跟 R02其实是一样的啦，哈。So by choosing the reference point to be equal distance from the two-line charge, that is R sub 01 equals to R sub 02. For example, the z-axis. So in this configuration, because the two lines are placed in a symmetrical fashion in this coordinate system, and the electrical charge carried by the two wires are of the same amount, of course, in opposite polarities. Therefore, the so-called zero potential reference is intuitively can be chosen as the z-axis, which is in the middle of the two wire. So in this case, by choosing the zero potential reference as the z-axis, then R sub 01, that is the distance between z-axis and the positive charge wire, is the same as the distance from z-axis to the location of negative charge. So by using the fact that R sub 01 equals to R sub 02, the potential established by the two-wire arrangement can be simplified as this thing. It's proportional to the amount of line charge density, and it's also proportional to the log value of R2 over R1. So for every constant value of R2 over R1, you can have what? You will have the so-called equal potential surfaces or equal potential lines. So let's put a test. So if you look from above, so this is the position . You look from above, so this is the y-axis, so this is the direction of the y-axis. Can you draw the line for equal potential? Well, if you look at the equation, you can see that if R2 equals R1, then what? Log R2 over R1 is equals to what? Equals to 0. Log of 1 equals to 0. So the condition is R1 over R2. So as long as R1 equals to R2, then V equals to 0. So where is the equal potential? So in fact, the whole plane, that is the YZ plane, the whole YZ plane is 0 potential. Because every point on the YZ plane have the same distance to positive wire and negative wire. All right? And equal potential surfaces can be drawn using that relationship. They are of different R2 over R1 value. So as you can see here, for example, what is the R1 over R2 value here for this case, for this point? Well, as you can see, R2 is larger than R1, right? So you will end up with a large number, a high voltage. And if you are looking at this place, what is the R2 of this case? What is the R1 of this case? For this case, R1 equals to what? Equals to 0. And R2 is some rational number. But if you divide this number with 0, then you will approach infinity. Okay, so this place will be the position of highest potential. And this location will have the V minimum. So this place is the V maximum based on this relationship. Okay? And so this is the result for two very thin wires. Very thin wires. And here are some further discussion about the result. As I already mentioned, the equal potential surface can be drawn with a constant R2 over R1 value. So if you supply the conditions, say R2 over R1 equals to K, and you substitute this result into this relationship, you end up with this relationship. That is the coordinate system in the Cartesian coordinate system. And you can find that this equation can be expressed in terms of equation for circles. And you can, based on this equation, you can find out the radius of the circle, and you can also find out the center of the circle. And K value is vary between 0 and infinity. Right? So the circles shall move. The center of the circle will move to the left as K value becomes larger and larger. And if K equals to 1, the center of the circle will move to minus infinity. If the K values becomes a little bit larger than 0, larger than 1, then the center will jump to the other hand of infinity. And it will move into this position as the K numbers goes from 1 to infinity. So that's the equal potential circles equipotential circles for this geometry. So now that in this case we see that the potential are different in this conductor. So providing that the data line 这个比较粗的线条代表的是导体的什么？代表的是导体的外径。所以你会发现在导体的内外其实还是有电位差。这件事情在静电场的时候是合法的，但是在实变场，也就是 AC 的那个电流的时候呢，就不行哦。在 AC 电流的出现的情况底下，导体内部是没有电位差的，导体内部不可以有电位差，不然它内部会有额外的电流就是说，所有的那个电流都会跑到导体的表面。这个东西有一个术语，你们可能有听过，叫做肌肤效应 （skin effect）。这个东西是你在处理实变场的时候就会变成这个样子但是在静电场的时候呢，你的电流是可以在导体内部的那这边我们看到的几个观察，我们看一下。第一个啦，就是圆心的坐标是这个正负 D 的那个位置嘛，然后电的那个电荷线的半径，我们刚才讲是 A 嘛，所以 A 跟 B 还有 K 的关系是可以被找到的，所以这个式子是要干嘛？这个式子是要来去找到电荷线表面的电压值。注意就是说电荷线的表面一定是一个等电位面、等电压面。不然怎么样？不然会有额外的那个电荷流动。假如那个导体表面的电压不均匀、不相同的话，那就会有额外的电荷流动，要流到它均匀为止。OK， 所以你的一个边界条件或一个强迫的一个解的话，就是你的那个电荷线有半径的电荷线，它的最外围必须是一个等电位面而这个电位值呢，就会是这一个从这边所得到的一个解所以从这两个关系的话，可以推导出 K 等于 D 正负 D 平方减 A 平方开根号除以 A，OK 所以 D 是圆柱的几何中心 ，B 是电荷分布的中心，而这是电荷表面的电压值。那找出这个电压值之后，就可以这边是整个解的那个状况了请你再稍微看一下那找了这个解的目的是什么？要算出电荷线的表面电压所以我们会把这一个刚刚的两个解。D 加减D plus and minus square root of D square over minus A to the square over A can be supplied because they are the 2K value. They can be supplied to the expression for the voltage. That is L sub 0, low sub L0 over 2 pi epsilon times log of K value like this. And here's an interesting fact that if you take in the product of the two values like the one over there, you found the product of the two is 1. So the solution for V minus can be replaced with minus of the blah 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 log D plus square root of D to the square minus A square over A. Alright? So the total voltage difference between the two can be expressed like this. So the final solution, because the voltage difference between the two wires is this, and it happens to be the same as the definition of our hypercosine. This happens to be the same as the hypercosine. So by taking the definition of C, which is Q over V. We can find out the capacitance. Per unit length capacitance is this. Now, it can be simplified as pi epsilon over archetypal cosine of D over A, which is essentially the result we have derived in this example. All right, so let's stop here.